So I'll start with this question. Suppose you have that f is this set consisting of these three things. Then is f a function? So there are two components to the definition of function. You have to be a set of pairs, which this looks like it is a set of pairs, and then there's that second condition that you have to check. So what do you think? Here's what I would say is the answer. I don't know. It's really unclear from here, right? Because, so let me move this down, because the condition for being a function is that whenever you have two pairs showing up as elements with equal first position, then their second position must also be equal. Now this looks like the first positions are never equal. Like here we have an x, here we have a u, here we have a w. I don't see a repeat in the first coordinate. But it's actually not clear that they're never equal. I mean, what if x equals u? No one ever said x doesn't equal u. Maybe it does. We have very little information about these variables here. So if x happened to be u and y happened to be different from v, then f is not a function, right? On the other hand, if x, u, and w are all different from each other, then there's no problem. Or if x and u are the same, but also so are y and v, then there's no problem. So this kind of discussion is difficult to get into when you don't know much about the variables. This is why I'm putting an assumption at the very top, which is that all the variables are distinct. No variable is equal to another one in this context. So assume x, y, u, v, w, k are all distinct. Distinct meaning, so this is many assumptions all packaged into one sentence. So distinct means not equal. So x not equal to y, x not equal to u, x not equal to v, and so on. And then y not equal to u, y not equal to v. So I'm putting that assumption there so that when you see different letters here, in this particular context, you can assume that you're looking at unequal things. Then, with this assumption, what would you say? Is this a function? Then I would say definitely yes. What would make this not, what modification would I make to this to make it not be a function? Here's one thing I could do, is repeat an input, so repeat u here, but then give a different opinion as to what the output should be. So something like this. Now the answer is definitely no, because we have violated that condition from way back here, this condition circled in yellow. I do have a pair where the first things match up, but the second things don't. And one violation is enough to make this not be a function, since the condition back here was a for all. So this is definitely not a function because the u's match here, but v is not equal to k. Let's go back to the one that was a function and discuss evaluation. So let's go back to this one. This one was yes, a function, assuming these things are distinct. Then what would you say f of x is? So the definition is that f of x is the occupant of a certain set, right? It's the occupant of the set of, let me use a letter that is not being used here for the bound variable. How about a? The set of a's such that x comma a is an f. But what is the set of a's such that x comma a is an f? So what is this set? What do you think it is? The set of things that sit in the second position with x. Y does, so y is in here. Does v? No, because u is not equal to x. Does k? No, because w is not equal to x. So this is the occupant of a singleton, and we just get y. So that is the sense in which f of x equals y. That's how we get that from our definition. Let's try another one. F of u. So it looks like f of u is going to be v. So the long-winded way to see that that's true is to see that f of u is by definition the occupant of the set of things that get paired with u as elements of f, which is the occupant of singleton v, which is v. But there's a quicker way to see that this is true, using essence of evaluation rather than using the definition. So let me show you the quicker way. If we want to know what is f of u, basically use theorem 51. Usually I just go to part 3 since that's kind of the powerful one. Sometimes part 2 is nice. Well, actually part 2 is nice here. So if I just show that a pair is in f, then I immediately get a statement as to what the evaluation of f at the left-hand position is. So I'm going to use part 2 here. So let me just use the theorem, and then I'll justify why the theorem applies in this context. So by theorem 51, part 2, f, since the pair uv is in f, we have, so this says if a pair is in f, then we have the second thing in the pair is f of the first thing in the pair. We have v is f of u. Okay, but there were some assumptions needed. So we needed, so we already checked this part, but we need also f as a function. And we already addressed that. Not rigorously, but sort of just by inspection, by staring at it. Of course, if you're asked to prove that something is a function, then you have to do a rigorous proof, and this would be annoying to prove. It would split into so many cases. But if you accept from here that yes, this is a function, then theorem 51.2 applies, and we have this. And to be fair, with the other way I was writing things, with the occupant version of things, with the occupant way of looking at proving that f of u equals v, when I was doing that, I was looking at this set, the set of a's such that ua is in f, right? And then I just stated that, or I just asserted that this is equal to singleton v. Okay, but that's something you would have to prove if you were in a context where you really need to rigorously prove that f of u equals v. And that would be super annoying. So you have some annoying proofs with lots of cases, regardless of what you do in this kind of situation. Luckily, this is not such a common situation anyway, where you just list finitely many elements like this. Usually this kind of setup is used for Math 8 examples. In practice, functions are defined in much more usable ways that don't require splitting everything into so many cases. Okay, but let's think about what goes wrong if we look at a non-function. So let me replace this example and then go back to the situation where we're looking at a non-function. So for that, I think I was just, instead of w, I was putting u here. So then this is definitely not a function. No, and I can say exactly why. Because uv and uk are in f, but v is not equal to k. That's because I assumed these are all distinct. So any given one of them is not equal to any other one. So this is why it's not a function. So then what happens if we try to do f of u? Like, what is f of u? Okay, if you just go with it and you try to come up with what is f of u, you come up with two sort of contradictory answers, right? On the one hand, you say it's v, and on the other hand, you say it's k. Really, there are two ways to look at what's going on here. So one is that you shouldn't talk about f of u in the first place. Just don't talk about this. Because this notation of a function evaluation, f of u, something of something, this requires that a certain assumption hold. It requires that you are looking at a function and that you are looking at something in its domain. We've got this part. Definitely u is in the domain of f here. U is in the domain of f. But the is a function part we do not have. F is not a function. So we just wouldn't talk about this. The definition of function evaluation does not apply. But what if you wanted to talk about it anyway? What if you were like, no, I'm just going to ignore this warning here and go ahead and try to use the definition of function evaluation. Let's just go and apply this machine and see where it takes us. Okay, well, then when you go to look at what is f of u, notice that we definitely cannot apply theorem 51, since that relied on the assumption that f is a function. So we have to use the definition directly and see where that takes us. So f of u, well, that's the occupant of the set of things that, when paired with u, like this, give you an element of f. So the set of second positions that go with u. Okay, but by inspection, which is not a proof, but just going with our guts on what this looks like it's going to end up being, this set actually consists of two things, v and k. So what's the occupant of this set, which is a doubleton? Now, a doubleton can sometimes be a singleton. Like if v equaled k, then this would be a singleton and there'd be no problem. But I'm in a context where I'm assuming v and k are distinct, right? So what is this? Well, when I had a singleton here, I knew that it was just whatever thing was living inside the singleton. I knew that because of earlier work with the occupant construction, this essence of occupant, that the occupant of a singleton is that one thing living in there. I'm now in a context where this is unavailable to me, so I'd have to go back and use the definition of occupant, which is going to start giving me nonsense. So the whole problem with trying to say what is f of u goes all the way back to this idea of what happens when you try to refer to the unique green thing in a context where you don't know that there is a unique green thing. There might be more than one green thing. So it's this whole problem of trying to extract the one element from a set that doesn't have one element. So there's no such thing as the one element. So that is the problem. Can you proceed from here and try to make this work out, just following along with the definitions, like trying to use the original definition of occupant? You can, but you're going to get nonsense. And if you want to play with that nonsense, that's fine, but none of the theorems you want are going to work. Namely, these theorems involving functions, this entire discussion, if you look at all of these theorems, they're all going to involve an assumption like f is a function. So here, f is a function. F and g are functions. Then soon we're going to define a notation which includes within it the statement that f is a function. Then you see that notation showing up everywhere. Assume this, but that's going to assume f is a function. So that is the formal problem with trying to evaluate a function, with trying to evaluate a non-function using function evaluation. This is so this maybe this sounds all kind of esoteric, but this is something that happens all the time, right? Like when people write division by 0 or something. The division symbol is a function, and writing something divided by something is evaluating the division function at a particular input pair of numbers. When the second number is 0, then that pair is not a valid input for the division function. So what happens then? Well, it depends on your formalism how that is dealt with. But for our formalism, we just say, no, we don't talk about function evaluation. We wouldn't talk about this at all. Even though you could follow the definitions and get nonsense if you wanted to. So here's another one. Let's modify this back and turn it back into the example that was a function. So where I had a w here. So now the answer is yes, it's a function. And then what is f of 3? How about that? What's f of 3? So what do you think? If x is 3, then f of 3 is y, right? If u is 3, then f of 3 is v. If w is 3, then f of 3 is k. But I don't know much about x, u, and w. I know that they're distinct, but I don't know that they're distinct from 3. It could be that none of them is 3. Then I would be trying to evaluate a function at a place that's not in the domain, and I would run into similar problems. I would run into similar problems with the fact that function evaluation requires that I'm looking at something in the domain. So this is only meaningful if one of either x, u, or w is 3. So let me put it this way. If 3 is in this set, which is the domain of f. So it gives the same kind of error that you would get if f were not a function, like we were just looking at. Okay, let's try another one. What if let's see, so I was changing this w into a u earlier to try to make this not a function. What if I turn this k into a v? Then what do you think? Do you think this is a function? So to check that it's a function, there are two things to check, right? First, it's a set of pairs, and second, this condition. Is it a set of pairs? Yeah. What about this condition? Is it the case that anytime two pairs are in there with the same first position, that they have equal second positions? Well, it looks like it is never the case that two pairs are in there with the same first position. I mean, unless you take a pair and the same pair. So let me put it this way. If you take two elements of this thing that are different positions in this list, so like the first and the third, then it's false that this equals this, right? So that is just not one of these cases that you would check. So from just staring at this, you can see that you never have first positions matching up, so you never need to check whether the second positions match up or not. The fact that second positions here are matching up doesn't harm the functionhood of this set. So this set is definitely a function. And again, that's not a proof, that's kind of just an inspection and a guess coming from looking at it. It should be provable that this is a function using the original definition, but since f is defined to be this list of three things, that means f is defined along the lines of definition 18.1 here, right? It's something that has this annoying or to it. That always leads to lots of cases in your arguments. So it would become a very long argument trying to prove that f is a function. You have to work with an arbitrary pair of things in f, right? And for each thing in f, like this pair being in f, when you assume that, there's three cases for what that is. For this thing in f, when you assume that, there's three cases for that. So there's like 9 total cases to think about. That's going to make for a long proof. But hopefully you're getting the idea here. Okay, well, here's also a fun one that we actually can do the proof for. So let me make a replacement here. Let's make f be the empty set. Is that a function? What do you think? So remember, the questions are, is the empty set a set of pairs? And the second question is does the empty set satisfy this condition here in the definition of function? So what do you think? So here's the answer. Yes. It is a function. When you think of it as a function, you can call it the empty function. This is something we can prove. The empty set is a function. Proof. So we must prove two things. It's a set of pairs, which we've discussed before. This is what it means to say that something here, the empty set, is a set of pairs. It means every element of it can be written as a pair. And we have to prove that that other condition way back in the definition of function, this thing, but with the empty set in place of f there, that whenever two pairs are in the empty set with the first position being the same, then the second positions are the same. Okay, but look at these implications. These are implications whose hypotheses are ridiculous, right? This implication and this implication. The empty set has no elements. And so these are vacuously true. It is true that none of the elements of the empty set take the form of a pair. And it is true that for none of the possible pairs of pairs in the empty set, if the first position matches, then the second position matches. There's nothing to check. So these are both vacuously true. And that's all we need to say. Vacuously true means these statements are just true. If I want to give a justification, I guess I would say by theorem 12 here. All right, so the empty set is a function. Its domain is the empty set, right? So it's a function, but you can't evaluate it anywhere. It just happens to meet the definition of being a function. Now, before I end this video, I also want to look at the ways of defining functions that you're probably familiar with before this course, which is by a formula. So sometimes people will do this. This is probably what you've seen before the course, is a function will be defined by a formula. Define f by a formula like this, f of x equals x squared. So like maybe when you're first studying parabolas or whatever, you'd be given a formula like this. So how does that relate to what we're doing? Can we do that with what we're doing? Definitely yes. Actually, what we're doing is something that's way, way more general than this. What we're doing allows us to define functions even when there's no formula available sometimes. But I would say for this that as it stands, the way I've written it, define f by f of x equals x squared, it's really incomplete. The domain needs to be known. The domain of a function is part of what the function is. So actually what people will say to complete this is they'll say something like define it by f of x equals x squared for all x in maybe the set of real numbers. Okay, so I'm definitely exiting our course right now. We have not defined this, and we have not defined squaring, but consider this to be a comment that sort of sits outside of our course, our proper course. So this is a complete and proper definition of a function, and here's what this is saying in terms of our language. It's saying define f to be the following set of pairs. The pairs are these input-output associations, right? So this is saying define f to be the set of pairs x squared running over all real numbers x. This is what it's saying. So the input x always gets associated with the output x squared. So when you see a definition of a function by a formula, it's basically just doing this. And I guess when one defines this, then one wants to prove that they have a function. But anytime it's given by a formula, it ends up being easy to prove that this is a function. It's not trivial, like it's something you have to do at least once. It's not immediate, but it does end up being easy. So that's why formulas work. And I hope you're also seeing why it's sort of a meaningless definition if someone doesn't give the domain. You know, just the formula x squared is not a function, right? That's just a formula. But then if you specify the domain, then you have this actual set of pairs where each element of the set is an input coming from the domain with an associated output. By the way, when I write something like this, notice that what's behind the barbell here, or the bar, is not a variable, right? It's a more complicated term. So this is, this is an instance of that shorthand notation that I was describing, where there's really a hiding existential quantifier in there.